Welcome. My name is Vince Couts, the author of the book Physics for Space Travel. Here is an image of the cover of the book. It includes the physics of both orbital mechanics and rocket physics, as well as instructions on how to use two very amazing and free simulators, Orbiter 2016 and Open Rocket. Today I will demonstrate the use of the Delta Glider. I'm just going to show you the essentials in order to do the exercises and missions in my book. You can refer to my book, Appendix B, for more information on the use of the Delta Glider. You can find a user's manual for the Delta Glider via a Google search. So I assume that you have downloaded the Orbiter 2016. Instructions for doing that are in my book in Appendix B. If you haven't done that yet, go ahead and do that. If you don't have my book in front of you, you can Google download Orbiter 2016. Okay, so assuming that you have downloaded Orbiter 2016, you'll see an icon that looks like this on your screen. So go ahead and click on that. This is a menu, so let's go through a few items. This is the scenario, the possible scenarios. You can actually save a lot of your own scenarios, and then there are a lot of scenarios provided by the developer of the software. Another very important screen is the parameter screen. These are the default values, and please do not change them. Keep it the way it is. Another important menu option here is joystick. I use the mouse and keyboard keys, and I'm able to fly actually quite efficiently and effectively the Delta Glider. You can purchase a joystick. And in fact, I do have a joystick from Logitech. It's a very good joystick. So it's not installed on this machine, but if you prefer a joystick, you can do so. But again, a mouse and keyboard are actually very easy to use with the Orbiter. Okay, so let's go back to scenarios. Double click on Delta Glider. Here are the Delta Glider scenarios. And the scenario you will run most often as part of this book is the DG MK4 in orbit. This is the default orbit of the Delta Glider. Okay, so what you're looking at here is you are looking at the cockpit of the Delta Glider. You are inside the Delta Glider. This is not my favorite cockpit. You can hit the F8 key to take you to various cockpits. And this is the one I like the most. It gives me the best outside visibility. But again, whatever suits you best. There are 3 different cockpits. These are multifunction displays, okay? And the way you select the multifunction displays is via this SEL button. Okay, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different multifunction displays. The one you will use most frequently is this one, the Orbit MFD. Others I use for orbital maneuvers and missions include the docking MFD, the align plane MFD, the sync orbit MFD, the transfer orbit MFD, and also the ComNav MFD. Okay, now strike the F1 key on the keyboard and you'll see an outside view. You can use the right mouse click button to look around. Okay, so this is the Delta Glider as it looks from the outside, and it's in an orbit around the Earth. The info key here is important, gives you a lot of useful information about the Delta Glider, including its total mass, the maximum thrust of its engines, some orbital information, atmospheric information. So the current orbit, there is no atmospheric pressure because the Delta Glider is above the atmosphere. This provides the amount of fuel in the Delta Glider. This turns on the rotational thrusters. This turns on the linear thrusters. You really don't need to fire the linear thrusters. The main engines, which can be fired with the Control Plus and Control Minus key, you don't need to hit either one of these buttons. It's just that's just the way it is. You will need to fire rotational thrusters quite a bit, especially for the mission in which you will rendezvous with the International Space Station. This provides you information about the heading or pitch angle. Heading, pitch angle, are the same thing. Right now, it looks like the pitch angle or the heading angle, again, are the same thing. It's pretty close to 0. Okay. The velocity vector or the direction of travel is indicated by this right here, circle with a plus inside. The caret right here, okay, this circle with the plus inside overlays right now the caret. The caret is actually the direction of the nose cone. Okay, so that right now uh, the thing is traveling in the direction of the nose cone. But what if we rotate the rocket with rotational thrusters? Okay, so I've got rotational thrusters on, and the way you fire rotational thrusters is the numlock pad. So 1 and 3 provide the yaw rotation, 2-8 the pitch rotation, and 4-6 the roll rotation. The 1-3 keys are the keys you'll use most often. I discuss in the book the difference between pitch, yaw, and roll. But let's go ahead and hit the 3 key. Okay, so you see now the nose is rotating away from the velocity vector. Okay, so the ship is traveling in this direction, but the nose cone is in this direction. Let's turn prograde off. This thing wants to keep locking to maintain the nose cone in the same direction as the velocity vector. So I'm going to put 1 back on. Okay, so firing rotational thrusters again. Okay, I'm going to kill rotation. Okay, and so this thing will, again, it's moving in that direction, but the nose cone is in that direction. Okay, and that's fine. When you are approaching another object you may want to rendezvous with, you'll want to point, you want to put this object, the nose cone, on top of where you're going and fire prograde thrusters. Now that's all discussed in the book. So let's get these lined up again. So I can either rotate this back to line up with the prograde velocity vector, or I can just hit prograde autopilot and the computer will do it for me. Okay, so again, now we're back to the default trajectory, which is a heading angle of 0. So these buttons are really important. These are the autopilot buttons. So prograde simply tells the computer to line up the nose cone with the direction of travel of the Delta glider. Retrograde will have the nose cone at 180-degree angle to the direction of travel. So let's go ahead and hit that. And you're going to see this the nose cone rotate by 180 degrees. And you say to yourself, well, why would you want to do that? The reason is you may want to slow down, right? So if you rotate the spacecraft and fire thrust such that the propellant is moving in the direction of the velocity vector, it will slow the ship down. Okay, so this is going to go to a full 180 degrees before stopping. Okay. All right, so there you have it. So that's nice. That saves you a lot of time. You don't necessarily need autopilot. You can do all this manually with the pitch, yaw, and roll keys. But this certainly saves you a lot of time. So let's go back to prograde and get the nose cone lined up again with the direction of travel of the spacecraft. Let's go outside the spacecraft and we can see the Delta glider rotating. All right, it's going to rotate back. Um, so the most frequently used autopilot buttons will include prograde, retrograde, NML plus, and NML minus. So this is if you hit this, the computer will align the Delta glider at a 180 degrees. Um, I'm sorry, at a 90-degree angle to the orbital plane. Okay. This will be in the opposite direction. Now, this is important when you want to change the plane of the orbit. That's discussed in great detail in the book. Um, let's see what else. Let's talk a little bit about the orbit MFD. Like I said before, this is the most important multifunction display. Uh, all of this is discussed in great detail in my book. SMA is the semi-major axis of the orbit. SMI is the semi-minor axis of the orbit. PER is the distance of closest approach. APR is the distance of furthest approach. RAD is the current location of the Delta glider in its orbit. ECC is eccentricity. When this is 0, you've got a perfectly circular orbit. Anything greater than 0, and it's not perfectly circular. The closer it is to 1, the more elliptical or the more oval it is. Greater than 1, you no longer have an orbit. You no longer have a closed orbit. You have an open orbit, uh, and the thing will escape the orbit when eccentricity goes above 1. T is the period of the orbit in seconds, how long it takes for, in this case, the Delta glider to make one complete revolution around the Earth. PET is the time until the Delta glider gets to the periapsis point. APT, time to the apoapsis point. VEL is the velocity of the Delta glider at this point. Inclination is the inclination to the plane here, and the plane here has been set to the ecliptic plane. So there are two possible orbital planes uh, that show up here, either the ecliptic plane or the equatorial plane. These are less frequently used, but they are used some, and these are discussed in great detail in the book. And when I use them in an orbital maneuver or an exercise, I'll remind you what they are. Um, the gray circle here is the Earth. The green circle here is the orbit of the Delta glider. Solid green point is the point of periapsis, right? The PER. Um, the hollow circles, small circle there, is the location of apoapsis, which is APR. This is the ascending and descending nodes, and I get into more of what that's all about when I discuss orbital plane changes. Again, in the book in great detail.